Okay. So, right. Um, where should we start?
Um,
I have here
so I
your.
guess, oh, sorry, go ahead.
Oh, I'm going.
So if I understand correctly, the way to solve this is two parts, right? One part is that we add the lint, and then the second part is actually make the fallback makes change the code such that the fallback happens from empty type to uh, the never type.
Yes. Um, more or less. Right. So now I'm trying to remember exactly the history here because I will be totally honest and say that I am not entirely persuaded that we should change this fallback. Uh,
Okay.
I'm trying to remember. There's been a lot of developments though that I see. Um, yes, okay, I remember. This is a good argument for why we should change the fallback, I guess. That this code doesn't work without changing it, or at least we need to do something in order to accept this code. Uh, and right, and the alternatives were kind of unfortunate. Okay, I remember now. So yeah, I guess right. So the idea was we believe that this fallback, that anyone who's relying on this fallback to unit, that there are very few, and that we should have some way to detect it and give warnings before we actually make any changes. Um, and so the idea was, right, if we can add a lint that seems to catch the cases we know of, then we can run some crater tests and see if anyone's turned the lint to make a hard error and see if anyone gets affected. So we can test our hypothesis, first of all. Uh, and then we can also help migrate those crates, right? And then once we have a lint, then we can actually go ahead and make the transition. Um, and the key thing is actually this lint is probably still something we want on even just all the time because it's a little bit, I think the pattern of code that we're trying to warn against is probably not recommended. Um, so in particular, what we're trying to warn against, if I'm remembering correctly, is something where I'm scrolling through your examples here. Uh, yeah, this is the classic one, dude, where, right, the fact that you panicked here winds up making this variable get inferred to the never type, even though that variable is totally live, right? Like affects the flow of live code. Do you understand how that problem goes wrong, how that example goes wrong, or should we walk through that?
So for this example, yeah, if we can go through that.
Yeah, I think it's pretty important to understand exactly what's happening. So why don't we go through it? So where did I kind of lost it now. Where was it? Yeah. So what happens here is this type underscore, this type parameter t rather, is specified to be underscore, which just means we're going to make a fresh type variable, right? And we're going to call that, let's call it question t. So let's see. walk through what goes wrong. So the type, the type parameter t gets specified as underscore. Underscore means make fresh inference variable. I'm going to call it question mark x, actually, so it's a different letter. So now that means that the type of unconstrained return, this is kind of, you could think of that expression here as being this expression, right?
Yeah.
And well, let's put the parentheses on it so it's actually the call. And that means this is going to be result of question mark x string, right?
Right.
And so that means that the type of x in the OKX pattern is question mark x.
Right.
And the type of, this is where it gets interesting, of error s, well, okay, the type of s is string. That's not really that interesting. Not particularly relevant. It's just true. But importantly, the type of, or to come back to this arm, this means that the type of, like this whole arm, the match arm, is question mark x, right? Does that make sense? Basically, because the type of this expression is x. And so the key point is the type of the match arm, error s, error panic bang s. Well, what is that? So this is going to be never, because panic has type never. But the thing that we do, at least today, is when the type of the expression is never, we create or I don't exactly remember where this occurs. We have to dig into the code to see just why, but I think it's something like this. First of all, these two types, the two match arms have to have the same type. That's not exactly true. What they actually have to have is there must be some type, let's call it M, that they such that both match arms can be coerced to that type. That's actually a rule. Does that make sense?
Yeah.
So, right, so in this case, question mark x must be coercible. Or the way we kind of handle that, you could think of it as like create a inference variable question mark m where question mark x can be coerced to question mark m. And bang, or never, can be coerced to question mark m, right? And
right.
what happens is somewhere, I'm not exactly sure where, part of the way we implement this part is that when the type of the expression is never, or exclamation point, we create a fresh variable, which I'm going to call v for never, and we mark v as diverging. And what that means is that if we get to the end of type checking this function and we still haven't found a value for v, we're just going to fall back to unit today and never type tomorrow, right? And the reason we do that is that you don't want to get errors. Like the reason we create this type is that then if we have this variable, like it can be coerced to anything. So it just kind of fits into the type system.
I see.
But the reason we mark it as diverging is you don't want the user to be getting weird errors saying we can't infer the type of this type variable that you didn't even know existed, that we made as a kind of artifact of how we handle never type coercion. So what ends up happening then is that now because let me move this up here somehow. what ends up happening is that we're not actually interested in never type coercing, but rather question mark v. And so what this means is basically we wind up unifying all of these variables. More or less. And so we're saying, okay, well, or sorry, not, what am I saying? Question mark x. There we go. We're saying that, okay, both of these match arms have to have the same type. This one is whatever that inference variable is, that's x. This one is the never type, and we'll make a variable for that, so that's v, and then m, well, m doesn't matter. M is just an intermediate thing. So now we said, okay, x is v, so now when we get to the end of type checking this function, neither x nor v are constrained. We don't know what they are. They could have any type and this thing would still type check. So we then try to do fallback.
I see.
And we don't have a fallback for x because it's a normal type variable. But we do have a fallback for v. And it falls back to the never type. So once we fall v back to the never type, we know.
So
go on.
Oh, sorry, I had this question that the type system will, so in this line, effectively we unify. So there it first went through X and saw that there is no fallback because it's a normal variable, but then it could find a fallback for V, and that's why it started to fall back on V, or?
Yeah. So
Okay.
the way this works, it kind of it kind of peels back some of the abstraction of how the type system is implemented. It's part of the reason I don't love fallback, but there it is. In other words, it looks at the type variable and says, has this variable been given a final value yet? And if you see two variables that got unified, but they didn't get assigned any actual type, the answer is no. And then it says, does this variable have a defined fallback? So neither x nor v have a final value yet. Even though they're unified to each other, they're not unified to any actual type. And only v has fallback. So v gets set to never. That also sets x to never because they're unified.
Right.
And now we have x being the never type. And that's kind of this weird outcome because now the fact that this arm panicked wound up turning this unrelated thing, which has, like the branch where the panic doesn't happen, has the never type. That's not what you wanted. That's strange, right? So that's what we're trying to lint for and say, okay, this is an unexpected outcome. Now, when we used to use the unit type, it was still unexpected. It was still a surprising result. However, it was kind of less harmful because, and this is a bit debatable, but at least in this example, it didn't cause as big a problem because it would fall back to unit, and unit is a kind of value that this function, maybe this function is actually a void function in practice, like this, we're transmuting some function pointer here, right? And maybe that function pointer actually is a void function in C, and so it kind of worked out by accident. And in practice, the way that the ABI actually works, like if you ignore the return value of a function, that's usually not a problem. It could have caused a memory leak or something, but so it was never great, but it wasn't so bad. But now when it gets inferred to never, that means the compiler can assume the function is never called, or at least that it can assume it never returns. Basically, the compiler can now assume all this code never executes because here you have a value of type never, and you could never have a value of type never. And that's not true. It does execute. So you start getting UB, weird optimizations, weird stuff's happening. Not great. And that's why it produced seg faults that didn't exist before. So what we wanted to do, my idea was basically like this. What was my idea?
So for your idea for the linting part was to like not take any expression but only the live one, and for the final fix, I don't think you had you had the mentoring notes for the final fallback avoidance,
Yeah.
but I might be wrong.
So my idea was it came out in two parts, right? The
Yeah.
first one was, can we identify can we identify the type variables who only got their value because of diverging fallback?
Hmm.
And that's a little bit tricky to do, but not that tricky. And that's what this PR does, this commit. Maybe we can look at it because I don't remember exactly what it did. Um, so I think what it did, oh yeah, so we can look at how this stuff, before we dive into the PR, let me pull up this function, I guess. How do I do that? This is the code that actually does fallback. Um, so this is probably the wrong version. Let's see if I can go back up one commit somehow. Will this work? Is it going to view what I want? No. Annoying. All right, that's fine. There's probably a better way to do this, but that's okay. So where's the actual fallback occur? Right here, I guess. What's this stuff? Yeah. So somewhere in here, right around here, this is like after type checking has finished, and we've figured out all the things we're ever going to figure out. Then we walk
So
through.
I have a request. Can you create a permalink and add it to that doc?
Yeah, let me do that.
Thank you.
So let's see. Where is this implemented? So right around here, we walk through the list of unsolved variables. So those that do not yet have a type. And we invoke fallback if possible, which I don't know where that's implemented, maybe in this module, maybe not. Yeah. And what fallback does is it basically looks at this type, which is a type variable, and says, first of all, is it an integer? You can ignore these cases. These come from integral literals and floating point literals.
I see.
Those fall back to I-32 or F64. And otherwise, is it a diverging type variable? If so, supply the diverging default, which is either unit or never, depending on the feature date. And down here, basically, we just don't do fallback for anything else.
I see.
What is this other
So,
logic?
so even today, there is a fallback for never.
Well,
Is that what you said?
yes, even today, so there is the never type is not stable. However,
Oh, okay.
we do introduce diverging type variables as the result of like return or break or things like that. Those produce diverging type variables.
See.
So, or if you call a function that returns never. The never, I guess I would say the never type is not stable in most places, but you can use it as a function return type.
I see.
So there's a few cases where you still get these variables. And so Yeah. So that's what the fallback actually does, right? And now we're basically iterating over and we're finding out if there's fallback. I guess I should scroll down a little bit below. If there is a fallback, then we try to equate to unify the type variable with its fallback. One interesting thing about this is that this can produce errors. Like
Hmm,
there might be, you might have had two variables that were unified but have incompatible fallback.
I see.
You know, in which case, applying both of those fallbacks could lead to an error. I'm
I
not
see.
actually sure how you can do that.
So I I have one might be slightly off topic question. So this unsolved variable, the unsolved variables I think we saw in the last function, that variable, like the list of that variable is taken in the scope of a block, like open curly braces, close curly braces, or at the function scope.
I don't think I understood your question.
Oh, so like the while we are trying to get the fallback for all these unsolved variables, unsolved types in, so
That's
in
at
the
the
first,
function level.
so I guess the first link, line 136.
Uh-huh.
So there was like we were going through the list of all these unsolved variables, right? And then trying to find a fallback for them.
Yeah.
So that happened. So this means that all the unsolved variables in the scope of that function
Yeah.
or in, okay,
Yeah. It's at a function level.
okay,
Um, right. So basically here we'll have done the fallback. Now we can we can now do a little bit more trait solving because now we actually know, like before there might have been traits that we weren't able to solve
I
because
see.
uh, because we had some unresolved type variables. Now maybe we've resolved those with fallback, so we can do some more trait solving.
I
Um,
see.
then it looks like we, oh yeah, okay. I don't know what's up with this. This is something to do with opaque types and seems a bit like a hack to me, to be honest. You can just pretend this code doesn't exist. Uh, but for our purposes, it doesn't matter because the idea is once you've done this next round, either you solved all the trait obligations or you didn't. And there's no more fallbacks to do because we're not introducing new type variables that have fallback.
Right.
So
Hmm.
if we can't solve them all now, we'll never be able to. Um, so then you start reporting errors. Um, I
What
guess
is
we
an
actually,
obligation?
oh,
I'm
an
sorry, this is a
obligation,
very
it's
low risk
something that
question.
you have to prove. So if you call like a function like this, well, even in our example, actually, scroll back up. This type t
Hmm.
actually has an implied bound that it's sized.
Oh,
Maybe as you probably know, which means that when I call this function, I actually incur an obligation to prove that question mark x is sized.
I see.
Um, and until I know what x is, I can't prove that's true. So I hold on to that obligation until I
I
can
see.
actually prove it.
Okay. Thank you.
An obligation is basically some trait thing we have to prove at some point.
I
Uh,
see.
so,
Thank you.
right. And so what did my PR do? So what I did, I don't remember, but let's find out. I basically just tweaked uh, that process to say, is this the right code? What is this? Um, right. So yeah, okay. So all I did was I remembered the set of I just store the set of variables that were unsolved to begin with. I run the same fallback procedure. Right. Then we do the trait solving. And then at the very end, we look and see, okay, of these variables that didn't have a type to start with, how many of them wound up having the type never type?
See.
Because those are the ones that, as a result of fallback, became never. And the thing is that it would include anything that was unified, like in this example, but it actually includes a somewhat bigger set because precisely because of those obligations, like
I see.
you can make some weird examples, like really the unified is probably good enough in practice, but the reason I did it this way is that you might have some function like where I have two variables, t and u, and I have some weird trait that makes them equal to each other. And it turns out that t, becomes diverging fallback, which then it's never directly unified with u until after the trait solving is done, but then we find out that u became never, right? So you could have something like this, or maybe like, I don't know, a less direct they're never actually unified with each other, but they're unified because the trait solving forced it that way, if that makes sense. So the idea was we'll just wait until the end, and we'll find all things that wound up getting a type that was never because of fallback. And that's the set of things that are kind of suspicious. And then what this PR did was it just warned if those types appeared anywhere. And that's obviously not right because we do expect those types to appear somewhere, right? Like they'll always appear somewhere. It's just hopefully they only appear in dead code, meaning code that comes after a return or a break or a panic or something, right? With me so far?
Yeah. Thank you. Yeah.
So my commit tweaks this to compute tainted types by save the variables before we apply fallback, solve trait obligations, then check those variables again to see which became never. Yeah, so, right. So the next step then is basically just, if you apply this PR, maybe it still applies, probably mostly still does, then you'll find that you get a lot too many warnings. So the goal is to pare back that warnings to some reasonable set. And what I was thinking of doing was trying to compute the live expressions and say if any live expression has a type that turns out to be one of these variables, that's a problem. And by has a type, I mean that the return type of the expression, like the result type, is one of these variables. I think that's what I mean. So in this case, like the type of X here, this is live, right? For all we know, that code can execute, and it's getting fallen back to never. That's a problem. So it's not. So in contrast, the type of this expression, that's also falling back to never, but we don't care because that expression is dead, or at least it's dead after that expression executes. but then the type of this match is also going to be live and equal to the never type, and that's a problem. So we would lint somewhere in here in one of those expressions, probably not more than once. That's the idea. And then the only question is, how can we compute what's live? And the answer that I was toying with is that we have already some stuff that we already track this information to a certain extent so that we can warn about dead code. So what I was thinking is, if we track all the code we consider to be dead, because that's probably a lot less than the code we consider to be live.
Right.
If we take all the code we consider to be dead and we throw it in a set, then we can find all the things that have a type that was affected by divergent fallback. And we can check, if any of them do not appear in this set, then they must be live, so then we can issue a warning. Probably not that much code, even. That was the idea.
Yeah, that makes sense.
In terms of, I don't know where I don't remember how much detail I gave in these mentoring notes about that. Let's see.
So if somebody wants to make this code work after we lint it, how will they make it work?
Well, the best thing would be if they can specify the type here.
Okay.
But there are different ways to structure it. I don't know, to be honest.
I asked this because I am so new, like I run into these kind of cases all the time.
I'd have to see the code, to know what's the right thing to be doing here. But so part of the problem is that this value is not being used in any way. Mm-hmm. So using the value might help. Why isn't it being used? I don't know. That's an interesting question. Okay. Yeah, I don't know. It's a good question. It depends a little on the situation. I know that the particular code that we took, that this pattern was taken from, was refactored to some other pattern that didn't have this sort of hazard.
I see.
I'm not sure what the other pattern was that they used.
So, I see. So the idea is to get the code that checks the dead code lint, and from there. Do you know? Okay, where that is? Warn always.
Yeah, I don't know. That's what I have to remember. So let's take a look.
So this is in the diverges enum.
So it's somewhere in this file, probably. Let's see. I mean, right. So there's this function, warn if unreachable, which gets called basically for everything. Some more links here. Let me show you. Here's an example. When we type check any statement, the first thing we do is call warn if unreachable, with the ID of the statement and the span and so on. Similarly, as we type check arguments, we do that. I'm a little surprised not to see even more calls than this, but they're probably in other files. So I think this is the function we want to modify. And I think basically what we would do is
refactor out the dead.
As we probably just here, after this if let is done, we can check what self diverges is set to. And if it's set to warned always, we can have some set and we can add it to that set.
Right, right. Makes sense.
And right, and so the idea of the warned always is like just all that warned always means is that we already issued a warning. So
Yeah.
it's still dead code. I think
There
that
is
will.
also a, sorry, there is also a maybe type in diverges. So for that, the code will still run into all those, like you said, that it runs into all sorts of problems because of all the compiler optimizations. So
No,
that
so
will still
maybe
happen.
all maybe means is in truth we never actually know whether something diverges, right? Because of the halting problem.
I see. Right.
So the reason it's called maybe is it means we have not. It doesn't obviously diverge. It might. It might be an infinite loop that we can't, you know, prove is infinite. So you can kind of ignore the maybe value, but this is still an imprecise. I mean, it's still a lint at the end of the day. Uh, I guess is what you were saying earlier. There are definitely
Yeah.
examples where weird stuff happens that we won't warn about. Um, I think the biggest problem I'm aware of with this approach, like one of the main goals of this approach is that it's local to the current function. So we're checking, is there live code in the current function that has this type?
Right.
But there might be live code that's not in the current function,
Hmm.
and yet it has this type.
Right.
And we won't catch that. So I can show you what that means. I mean, if you just take this example and tweak it a little bit, uh, actually, it's a little bit hard. Not so easy to tweak it. Let me think. Well, I don't quite know how you tweak it. We have to find an example. But the key thing would be that you don't. If you wrote something like this won't actually cause the problem. But
I see.
but but it won't cause the problem, but still, maybe there's another way to tweak it such that it would. The idea would be if somehow this still wound up getting fallback, then now the place where a value of type T occurs is actually inside the function and not visible to us from the caller.
So
We won't issue a warning.
I see. So in this case, it won't cause that issue in 180 because the type of, I don't know what that, like the unit type is already defined, right?
Yeah,
It is
exactly.
not X anymore.
Yeah,
So we
actually,
know.
no
Oh.
fallback at all will occur in this example because
Mm-hmm.
we'll unify a unit with the type of this panic, and we won't need to fall back because now it has a type unit, so it's fine. So actually, yeah, I don't. That's why I think this lint is good enough. Is that it's kind of hard to make an example, but I think we had some. Maybe if I dig in, they were more theoretical, but we came up with some examples of. On the other hand, there's lots of examples where maybe I think the examples might be stuff like this. I don't know. Where like you know something yeah, I think something like this might do it. I have to look, but the idea is here the type type of OK is results question X. Well, sorry, if this is X, if underscore is X, the type of this is like question A, and the type of the error call here is result question B, question mark Y, or let's call it V, where V is diverging. So we wind up with the type of this expression being the result of this, basically. And I wouldn't produce a warning here because the type of the expression, like no live expression actually has the type question mark V. You see what I mean?
Right.
It has a type that wraps question mark V, but it's not question mark V itself. And I wouldn't want to warn on that precisely because this is often a source of false warnings if we do that. Because like it often happens that like basically there are many functions where this would, if you don't know what unconstrained return actually does, it might just do something like this,
Right.
Now everything's fine. In fact, that's very common to have an unconstrained type here precisely because it never gets produced. But we can't tell. It might still use T in some weird way. So I'm betting that usually unconstrained return values that aren't directly returned are actually not used at all.
I see.
That makes sense.
Yeah. So the lint might be good enough for people to just refactor the code.
Yeah. So the bet is that an unconstrained return value like T here signals data that is never used. E.g., this function could return OK. But in this case, that is not true. Yeah, and so we did directly observe. I mean, it's a little bit more than a bet. Like we definitely observed a lot of false negatives. I don't think we observed a single case where this actually happened and was a problem.
I see.
So. Yeah, there we go. I'm going to put this example in the tracking issue, though. I think it's a good one.
Okay.
That makes sense. Any questions?
Yeah,
about
it totally makes sense. Yeah, thank you. Thank you for taking time and explaining it in a sync meeting.
Okay. Then do you think you'll have time to poke at it? I guess.
Yeah, sure. I'll try this weekend.
Okay. I was gonna say, I guess step one is probably like rebasing this commit, I suppose, or that commit, and then trying to collect the dead nodes.
Yeah, makes sense.
The one thing I think we should, well, there's not much we can do about the dead node collection, I guess. It would be nice. I'm betting that this won't have much impact. We'll have to test that, perf-wise, I mean. But one thing I think we should be a little careful of is, and I think I already coded the lint this way actually, that we don't want to be going through and looking at the types of all the expressions. We basically just don't want to introduce any big loops that are not running sort of proportional to the amount of dead code or something. I expect most functions just won't have any diverging fallback at all. So we can kind of
Yeah.
use that to say, even if there would be no effect in the, don't even enter the loop if there is no diverging fallback, because clearly we're not going to issue any lints, stuff like that.
Yeah, that totally makes sense. Yeah, we can do some perf testing to see how much of an overhead my
Yeah,
changes bring.
yeah, we'll do a
Yeah.
perf test. We'll see if it matters.
Okay. Yeah, sounds good.
All right, thank you.
Cool. Thank you so much. Thank you very much.
Do you object if I post this to YouTube and then I can throw the link in the tracking issue?
Oh yeah, yeah, absolutely, yeah. And feel free to, yeah, people can modify, they can view HackMD. It's totally, it solves my purpose, but it's also for other people who might want to look at it.
All right, talk to you later then.
Thank you. Talk to you later. Bye.